Okay, welcome to our third presentation live from the Markley Center in Boston, Massachusetts. We're going to show you a absolutely phenomenal, first of a kind, first in history, brand new power source where we're creating a new state of hydrogen from reacting atomic hydrogen with a catalyst. It's an entirely novel, groundbreaking, earth-shattering, disruptive, totally revolutionary new form of power. We're very, very happy and pleased to be here today to share that with you. So, don't really like to talk about myself, but let me just give you some background. So I am president, CEO, and founder of Brilliant Light Power. I have a degree in chemistry where I won a lot of awards. Graduated first in my class, won a lot of awards in chemistry and physics at Franklin Marshall College. Went on to in the interest of developing technology at Harvard Medical School, did a lot of technologies, everything from artificial intelligence to gene sequencing, new type of magnetic resonance emitter, using Mossbauer effect for a new type of novel cancer therapy. I've patents and publications in all these different fields. And particularly one of the things I was taking MIT at classes, particularly electrical engineering program, simultaneously with the Harvard Med education, and I had a professor there I was working on that gave me a paper that related to problems I was solving for in the Strategic Defense Initiative Organization program for shooting down ICBMs, intercontinental ballistic missiles, and particularly he was looking at the issue of why accelerating charges radiate. That's a fundamental problem of physics that led to the divergence of current atomic theory from classical physical laws to a purely mathematical model called quantum mechanics. And in particular, he's showing why, using physical laws, why accelerating charges radiate. And I took the converse of that and then applied that to the electron in the atom, which is constantly accelerating, yet the atom doesn't radiate. And that led to the development of an entirely new paradigm in physics, whereby physical laws exactly solve atomic problems, subatomic problems, molecular problems, macromolecular problems, and problems even up to the large scale structure of the cosmos, even predicting the acceleration of the expansion of the cosmos before it was observed. So, so this new state of hydrogen was predicted from this theory. And fundamentally, how it works. It's a primary, it resulted in a new zero pollution primary energy source applicable to essentially all power markets. It works by creating a new state of atomic hydrogen by reacting the atom with an energy acceptor of exactly 27.2 electron volts, thereby forming a new lower energy orbital of the hydrogen atom that we call Hydrino. It's a more stable chemical form of hydrogen with tremendous energy release. And the reaction is captured in a device called a SunCell that I invented. And it's equivalent to the internal combustion engine burning gasoline. But in this case, we're using hydrogen to form the Hydrino form of hydrogen and release immense amount of power, 200 times the energy of burning. And it's vastly superior. And there's no pollution or no product that's harmful to environment. So there's the discovery of the Hydrino. We've discovered Hydrino, his existence has been validated by independent labs. We actually have 22, and actually greater than that, more than 22 spectroscopic and analytical techniques that unequivocally prove the existence of Hydrino. We have Hydrino in a bottle, which I have here. This is a chemical composition called gallium oxyhydroxide, which has trapped in the latest molecular Hydrino. And it has a very unique characteristic that it has a paired and unpaired electron in a single molecular orbital and has a electron paramagnetic resonance signature that you can see by the corresponding spectroscopy that I'll talk more about later that dispositively identifies this new state of hydrogen among other techniques. It has signatures that are unlike unlike those of anything ever observed previously. So it's unique and characteristic and identifies Hydrino. So the SunCell is, we've done a lot to simplify it and make it so it's commercially manufacturable in scale. It comprises a hydrogen and catalyst injector that processes the atomic molecular hydrogen and atomic hydrogen fuel. It creates the catalyst by a chemical reaction in trace amounts. And then we have an electromagnetic pump that injects a separate system molten metal against the counter electrode, and we run a very, very high current through that to create a plasma and hydrogen that forms the hydrino during that reaction. Ordinarily, the plasma would not form if it were not for the very energetic reaction of forming hydrinos. It's an energy release at 200 times, and it emits extraordinary high energy and high power light in the range of shorter wavelength and ultraviolet that ionizes the gases inside. So we get essentially 100% ionization to sustain and maintain that plasma to form hydrinos. So in today's demonstration, we're going to show the proprietary SunCell. It's been validated by leading experts. For example, a leading combustion engineer, PhD at Rutgers, an expert in combustion engineering, the chairman of the Department of Physics at UNC Asheville, and another PhD from Berkeley that is noted as one of the best heat transfer experts by anyone I've ever talked to. So we have 250,000 watt power, and more than that in terms of validated, cooled, continuously producing steam in systems, and the other in black body radiator type systems. We have SunCells in field trials that we're doing internally now that produce on the order of 300,000 watts of power, and we've recently invented a window to release that high optical power of intensity more than 4,000 times that of the sun to illuminate photovoltaic converters, particularly thermal, what they call thermal photovoltaic 3,5 junction cells and single crystalline single junction cells for converting high intensity light into electricity. So it has extraordinary power density. It's unsurpassed in terms of its capability in generating high power. For example, a gas turbine's about 1,000 watts per liter, about a kilowatt per liter. In this case, the SunCell has been validated at 5 to 10 megawatts per liter. Extraordinary high power. And in the optical power experiments, we've gotten 20 million watts from a 10 microliter shot. Unsurpassed power densities in terms of a pulsed power. And then we've worked for about 4 years on engineering systems to harness that extraordinary power in terms of these continually operating systems for both thermal and electrical power on the order of several 100,000 watts running continuously. So this required an enormous amount of work. It started out in 1991. It was actually about 3 decades of work, $120 million for this program. We had hundreds of electrolysis cells, and we did permeation cells. We actually created a plasma and hydrogen using thermal power, and the plasma persisted even after all electricity was turned off, showing that it wasn't field-driven. It was actually a chemical reaction. Sustaining a plasma and hydrogen was unheard of. This experiment is actually, and this technology is actually replicated by a double director of both Jülich National Lab in Germany and the Institut Niederplasmusik. And then we went on to other types of cells, microwave cells, Bienecker, there's McCurl and Evison, and all kinds of different cavities. There's RF, there's glow discharge, there's inductively coupled, capacity coupled, like every imaginable type of plasma cell across the gamut of frequency ranges from acoustic all the way up to gigahertz frequencies. Switch from that into solid fuels, another further advancement using chemical energy to try and increase the gain, using chemical energy to create the atomic hydrogen catalyst. Had 6,000 solid fuels that we tested, did all the thermodynamics, the chemical characterization, analysis, and achieved up to 1,000 watts per liter. There's impediment in terms of regenerating. The idea there was the goal was to regenerate those the chemistry using thermal power produced by the reaction. There's some kinetics issues there in terms of creating an impasse in terms of competing with fire. So we segued that. Another type of platform invention, an electrochemical reaction. It generated the atomic hydrogen catalyst, an electrochemical cycle. Got 40 times the current out that we input. Double chair professor at Caltech, MIT PhD, Samina, Fortune 500 company. Many Ensor, other companies and experts in electrochemistry and thermodynamics validated it. power couldn't be scaled. So we moved on to another platform, and this turned out to be absolutely phenomenal. It was based on a theoretical prediction that we could form an arc current in plasma that rapidly create higher kinetics, rapidly increase the reaction rate, and turned out to be so incredibly effective that it caused an explosion, unlike anything that we've ever seen before. In terms of, it's 10 times more powerful than TNT with only 1% the shock wave coupling or energy coupling into the shock wave. So there led to 22 hydrino identification methods, and then ultimately we engineered it into commercially viable power systems. One of which you're going to see today is SunCell at about 150,000 watts. It's been validated up to 250,000 watts and higher at continuous steam power generation. We're going to show it today at a level which is commensurate with the data center we're in, so we don't create too much steam and a thermal load on the systems here. So overall, 120 million invested. We have over 100 peer-reviewed 100 peer-reviewed publications, patents worldwide. The theory is complete and reviewed. It analytically solves essentially all major problems in chemistry and physics, from the scale of subatomic particles, quarks, all the way to the macro scale, the universe, cosmos. We have this new state of hydrogen in a bottle, and we have the SunCell operating at commercial scale with commercial designs. This is showing a window into the SunCell, and this is a new technology we invented. It doesn't metallize over. Usually in plasma physics, you have metallization of the window. So here we can allow the extraordinary bright light from the SunCell reaction, creating a black body radiator in the range of 3,000 to 5,000 degrees Kelvin that would correspond to intensity of light emitted of more than 4.5 thousand times that of the sun. And then that would be illuminating photovoltaic cells that are designed to accept this very, very high intensity light. So you can see the blue hue of this. This is characteristic for a hydrogen plasma. This is greatly attenuated because of the extraordinary intensity of this light. So moving on, we're going to describe the hydrino, and particularly what is a hydrino and how it's formed. It's formed by a catalytic reaction of atomic hydrogen. So we have atomic hydrogen reacts with an energy acceptor, and that's a resonant non-radiative energy transfer. So there's a transfer from the hydrogen atom, and you can see here it's depicted as a thin membrane or bubble around the proton. The electron cannot be a singularity, that is a single point. Otherwise, you'd have a positive and negative end to the atom, and any motion would cause radiation. In this case, the electron is solved as the solution to the electron turns out to be a continuous current density function that reproduces all the phenomena of electron spin, the Bohr magneton, electron magnetic moment, the Stern-Gerlach experiment, the Lamb shift, fine structure, hyperfine structure, lifetimes of excited states, etc. All these are analytical closed form expressions from electrodynamics. So we know exactly what a hydrogen atom is. We know exactly what an electronic excited state is. That's a combination of electron, proton, and photon. The photon carries electric field and partially cancels the electric field between the proton and electron, allowing it to go to an excited electronic state, which is unstable. And there's an electrodynamic reason for that, particularly the interaction of photon and electron creates a radiative dipole. So it spontaneously radiates back to the end as one state. Conversely, energy can be transferred from the hydrogen atom to an energy acceptor, which is a large amount of energy. It's on the order of 27.21 or a multiple thereof. That causes the energy acceptor to become ionized, and you have ions and electrons, free electrons being formed. And after that energy transfer, the electron then moves closer to the proton due to an electric field created between at the electron inner surface that causes it to be bound tighter. There's the electric field goes up as an integer due to the photon electric field that's created inside this resonator cavity that comprises an electron and a proton. So that radiation is emitted as continuum extreme ultraviolet light with a 10.1 nanometer cutoff, or about 122.4 electron volts in that secondary step. That radiation is seen all over the sky at about 3 to 4 times higher intensity than all the known emitters in the universe combined. And it's coming from dark matter forming regions. And that particular radiation explains enormous amount of hereto inexplicable problems in astrophysics, which I'm going to cover here a little bit later in the presentation. Third step is where we had a tremendous breakthrough in terms of kinetics. So the catalyst loses its electrons and forms ions electrons. So one way to recombine them is to apply an arc current. Arc current is an applied electric field that goes through the plasma and creates a condition whereby the electrons and ions recombine. Arc current is a very unique state. It typically you have V equals IR, that joules per coulomb is volts. Volts equals current times resistance. So the higher the current, the higher the energy required, and thereby the higher the voltage. Arc current is just the opposite. The joules per coulomb actually become lower. That is, the voltage drops with higher current in an arc current state. That gives the condition for positive feedback and extraordinarily high kinetics. So the hydrino, as I said, releases 200 times the energy of burning hydrogen. So you can actually look as water and equate the energy content of water to other fuel sources, particularly wind and oil and coal. One thing very interesting, if you look at it in terms of a Tesla size car, not a Tesla per se, because the Tesla you could charge the batteries, but in this case we would replace the battery with a SunCell. So the liter of water could take the Tesla size car 2,200 miles. So we would extract the water by doing electrolysis. So there's 200 times the energy gains. That cost you 0.5% of the energy released, but overall you have 99.5% of the energy available for powering a load. Extraordinary energy compared to other sources as well. If you look at hydrino, 25,000 megajoules per kilogram compared to, say, natural gas, 47, and gasoline, 45. Another interesting thing about going back to the car application, if you look at a car in terms of the Tesla battery can only withstand very, very high current discharge for about 10 seconds. So the ludicrous mode is only for 10 seconds, it destroys the battery. For commercial applications for power, you could look at powering auxiliary loads or doing vehicle to building charging and other distributed, using that car, for example, as a distributing charging asset. So in that case, how much energy can you get and how much power? Turns out the liter of water, the 22,000 mile equivalent, is not for 10 seconds, but it's for 24/7, 365. And typically this equipment's rated for over 20 years, pretty much maintenance free. So it's an entirely different scenario. And it's about 1% the weight of a battery. So there's a number of techniques that show this hydrino. As I said, there's 22 or more. And in each one of these categories, there's actually more. Like the Raman, there's a 785, there's a 633, there's a 532, there's a 442, there's a 325 laser, all kinds of different massive amounts of data we've acquired on hydrino. I'll focus on 3 particular tests. Electron paramagnetic resonance, typically looks at free radicals or composition of matter with an unpaired electron. The hydrino is very, very unique. It has an unpaired electron and a paired electron in the same molecular orbital, and they can interact with each other. And we see that characteristic signature, particularly spin flip transition. We see spin orbital coupling between the unpaired electron and a paired electron, and we also see the fluxon linkage. That's the magnetic flux. When you apply magnetic field to the hydrino, you see flux linked in the units of magnetic flux quantum, which is h over 2e, Planck's constant, divided by 2 times the fundamental electron charge. We also collect gas cryogenically. You can run a cryo pump at near liquid helium temperature or below, and you can liquefy this gas, and you can put it on a gas chromatograph, and it migrates faster than any known gas. The prior fastest known gas is being helium and hydrogen. It also has a higher thermal conductivity than any known gas. What's very interesting, in addition to electron paramagnetic resonance spectroscopy, you can use Raman spectroscopy, which typically looks at the rotational and vibrational energy of molecules. In this case, if you look at the rotational energy of the hydrino molecule, it also shows the same what they call hyperfine splitting or fine detail due to the spin orbital coupling and fluxon linkage that you see in electron paramagnetic. But the energy scale is 1,000,000 times higher. And also that's also further seen in electron beam excitation emission spectroscopy. So we have three techniques that show a very fundamental information about the electronic structure in a hydrino that is prior to unknown. There is nothing known to man that has that type of signature. There's characteristic hyperfine lines or other characteristics in the spectrum. So we another aspect of this slide is you can see there's many universities were involved in these analyses. For example, we do the Raman, XPS, TOF Sims, and other types of analytical tests at other labs like Lehigh University, Princeton University, Duke University, Case Western, and others. So all these have been, all this data has been done externally, and where you do see brilliant light power, for example, that actually has multiple expert validators have come in and used our unique equipment with NIST calibrated light sources and other standards that absolutely validated and confirmed this new state of hydrogen. So I'm going to go on to, there's a paper in publication. It's available at this link. And it's quite extraordinary. It's done by one of the top electron paramagnetic resonance spectroscopists in the world, Dr. Hagen. He's done this entirely on his own. We only supplied the samples and the theory. And so this is the name of the paper. It should have a very dramatic impact in the academic community when it's published. So there's some interesting features. This is a singlet, typically indicative of a free radical that is a composition of matter having unpaired electron. And then if you run this spectrum for not a couple minutes, but you run it for days, which is pretty extraordinary. You see there's two features that are revealed, and particularly these are due to the spin orbital coupling of between the paired and unpaired electron. And this shift is again another exact predicted value of something called the G factor, which has to do with the energy of the transition electron in a magnetic field. That's exactly where it's predicted for this molecular species. Even going into these bands, these two split bands, if you look into those, we even further detail on further data acquisition time. You see that it's split in a number of hyperfine lines. These are the lines due to magnetic flux linkage in units of h/2e. These are the same type of transitions that are seen in a superconducting quantum interference device, which also links flux in units of magnetic flux quantum. But rather than some huge macro electronic component with very large cooling requirements, liquid helium cooling requirements, it's a single molecule, 64 times smaller than molecular hydrogen, which enables finally a photonic laser where you're using molecules and atomic scale type devices like you'd use, for example, for logic gate, for memory element, magnetometer, and others. And also the very high energy rotational transition in the molecular hydrino can be used as a molecular laser of unsurpassed power and high energy. So there's many applications of this, and these features show aspects of this molecule that can be exploited for unique chemical applications. So then to summarize the different transitions, you can see the total acquired data up here in frame D, and this has a number of different hyperfine bands in it for different spin orbital coupling quantum numbers, and then they're split by different fluxon linkage quantum numbers, and you can see below it the simulation and its identical match. This is a simulation from the classical theory that actually solves the hydrino molecule exactly. It gives its bond distance, it gives its rotational frequency, its vibrational frequencies, it gives its ionization energy, it gives all its scale, it gives nuclear magnetic resonance signature, it gives its quadrupole moment. All these things in the hydrogen molecule and molecular hydrino states are solved absolutely exactly. Even hydrogen molecular excited states in analytical closed form expression, which you can absolutely not do recurrent quantum mechanics, which is basically mathematical algorithm that spits out a number. It doesn't really solve what a molecule or atom or anything is. In fact, it says it can't even really exist. All you can look at is numbers because the universe is math and there's no determined physics on the atomic scale, and that's not true. it turns out the classical laws do apply at the level of the atom, as this data confirms. So why is there a controversy? Again, there's still debate, and actually there's greater and greater realization that reality has to be addressed on the atomic scale. For example, you can look at electrons in superfluid helium, and they actually exist before they're measured, or they wouldn't have different migration times. So there's not a, it's really nonsensical to talk about the electron being a wave function and being some figment of invention of mathematics. It really has a real structure, and it really has real energy and position even before it's measured. So the whole premise of quantum mechanics is that reality can't exist on the atomic scale. Not you can't measure it and there's some uncertainty, but it's really absolutely uncertain in terms of its reality on the atomic scale. Completely implausible as a physical theory. It's been used because there's nothing better until now. It turns out that free electron lasers, synchrotron radiation, and plasma physics obey classical laws. So those are free electrons. And why don't those free electrons, when they bound to a proton, all of a sudden lose their distinguishing characteristics and all of a sudden become pure math? It's totally implausible. The macro world is made of electrons and atoms, so it only stands to reason they have to obey physical laws as well, and they absolutely do. It just wasn't known how to solve them. Even very odd aspects of quantum mechanics, like spooky action and distance, where they see across miles photons having perfect correlation in terms of their angular momentum, that just proves that physics does exist on the atomic scale. Quantum says it doesn't, so therefore there's a spooky action. In fact, it does. And all that does is confirm that physics is real at the atomic scale. So all these things, delayed choice Gedanken experiment, Wheeler, where they explain it as light going back in time and following multiple paths and interfering with itself, all that is total nonsense. It turns out that physics absolutely is obeyed and it's completely practical, predictable once you understand what a photon is or electron and have exact physical solutions for them. Double slit, it restores causality and locality. Everything is absolutely predictable from intuitive physical laws and simple math. So once you have an explanation, that is, there's, for example, let me give you an example. So the speed of light was predicted by Maxwell as the inverse square root of the permeability times the permittivity of free space. And that at the time explained an enormous body of data that was there, that was before that time inexplicable. In the case of Hydrino, the same applies. The solar corona around the sun, the gases around the sun, appears to be 2 degrees, yet there's carbon monoxide molecules in the sun, other indicators that's not thermally that hot. So it doesn't really make sense that it's a thermal ionization mechanism that creates the high energy ions in the sun. In fact, what causes it is the release of extreme ultraviolet continuum radiation from the Hydrino reaction. And even Bahal, you can see this big vent where the solar corona is active, that the sun in an active corona state can produce the entire power output of the sun, about over 3 times 10 to the 26, 3 divided by 26 zeros, watts of power. And the transients are very, very fast. So Bahal, in his Nobel lecture, said that for the solar neutrino, he won a Nobel Prize in solar neutrino physics. He said that there had to be another power source in the sun. And it stands to logic, because nuclear reactions require 100,000 years to propagate power to the surface of the sun. And the transients of the sun are very, very rapid, and the powers, as I said, transients are on the order of the power of the sun itself. So it just stands to logic. There's another power source, and the particular constituents of the sun and the condition they're in can propagate the Hydrino reaction. You can see a continuum band of extreme ultraviolet light at about 91.2 nanometer cutoff. Those same types of bands that we see in our lab, particularly 10.1 cutoff, and that radiation seen from all over the sky as extreme ultraviolet light, again, as I said, 4 to 5 times more intensity than all the emitters in the universe combined. If you look at a white dwarf star where it doesn't have a corona but has a very high gravitational field, so the gases don't exist around the white dwarf as they do in the case of the sun, so you don't have a corona. So this light is not absorbed by those gases. You actually see the Hydrino continuum bands, for example, 91.2 nanometers at 22.8 nanometers and 10.1 nanometers. Those are exactly predicted for Hydrino transitions with continuum radiation in these spectral regions. Otherwise, there's no explanation for these type of phenomena. In addition, if you look at the distribution of something called dark matter makes up almost all the mass of the universe, but it doesn't absorb or emit light. That is a characteristic of the hydrogen that we are forming in our lab. That is, it doesn't absorb light, but you can see it by rotation, vibration, and other types of spectroscopy, as indicated previously. So the Hydrino, we feel, is in fact the identity of dark matter. And the evidence for that is it has the same distribution as ordinary matter, that is, which is predominantly hydrogen. And when you look at galaxy collisions like Abell 520, it behaves like hydrogen. Moreover, if you look at spectral signatures, for example, the diffuse interstellar bands, there's about 500 spectral bands that you've seen from interstellar media and all over the universe that have defied explanation and don't match anything known on planet Earth. We have about 25 spectral lines from our Raman data that match identically the diffuse interstellar bands. Moreover, the theoretical predictions for these rotational lines match all the lines of the diffuse interstellar bands. So it explains a lot of things. It explains solar physics, it explains interstellar media, which is phenomenally hot, but yet the interstellar media has been measured to be extremely cold. It explains data from white dwarf stars, and we feel it is the identity of the dark matter of the universe. And there's very many other astrophysical problems that are solved by the realization that there's a new state of hydrogen and the discovery of new state of hydrogen. So I'm going to go into the SunCell. The SunCell is the internal combustion engine equivalent for gasoline, but we're vastly superior. You're looking at about $30 to $40 a kilowatt capital cost. So we're looking at steam boilers at 250,000 watt scale, and then electrical devices about 150,000 watt scale. So SunCell is a source of power, and then there's different components that go onto that harness that power. Particularly the SunCell has a molten metal injector. It has this fuel processing system on the top, which is a glow discharge. And the reason being is we've ran black body radiator emitting SunCells that run at very, very high temperature. But when you put them in water and you have the walls at cold water temperature, then it won't work. And the reason is because it doesn't get hot enough. To solve that problem, I added a glow discharge, invented a glow discharge reactant preprocessor. So glow discharge is like a mercury light. So you apply a high voltage and then you get the electrons and bombard the gas that's inside and ionizes it. So you get an ionized composition of matter called plasma. And that flows into the main reaction cell chamber and then propagates the hydrino, or supplies fuel to the hydrino reaction. Also, there's a molten metal injector that creates this arc current state that I talked about that recombines the electrons and ions so you can get very, very high kinetics. The plasma and molten metal that we have in this cell are very, very effective at heat transfer, so we don't need an external heat exchanger like a shell and tube boiler design or air heat exchanger. And the heat is transferred across the wall into the water and causes the production of steam. And then the pressure in this reactor can be controlled by controlling the size of the aperture on the outlet of the steam boiler to create between half an atmosphere and 15 atmospheres, which is the standard pressures in commercial available boilers. In addition to the boiler, we have another type of heat exchanger, which involves heat pipes that are embedded in a series of thermal fins, and we blow air, atmospheric air, through these fins that accept or transfer heat from the wall of the SunCell to these fins, and it heats up the hot air for variable temperature from 100 degrees C to 500 degrees C. Now, moving on to one of the most exciting applications is the thermal photovoltaic converter. So this is one design, and this is something that just came into to being practical very, very recently. We spent about $20 million on this program about 3 years, and the goal was to heat a black body radiator. That is like a dome of the cell, make it of carbon or tungsten that can refractory material capable of operating extremely high temperatures and basically acting as a light bulb. So you can think of a light bulb, say 100 watts, and think of its area. You make it 1,000 times that, you got 100,000 watts, or you make it 2,000 times, you got 200,000 watts. So this would basically be a light source that would illuminate the photovoltaic cells and then would be converted into electricity. That turned out to be very, very difficult problematic milestone. The material considerations, differential thermal coefficients expansion, sealing problems, chemical compatibilities. So segued away from that program and then developed the thermal application, in particular one you're going to see today. But there's been a breakthrough here recently that became tremendously important in terms of bringing that program back online. I'm going to come back to that in a second. So we're going to show the demo now. Okay, we're going to switch to the SunCell demonstration. That is the thermal application, about 150,000 watts of steam production, and I'll explain that to you here at this time. So what you're seeing is water being boiled off from the surface of the SunCell, and it has on the very top of the cell, you can see that there's lines into the cell. I'll go and show these. So there's a hydrogen gas line, and then there's a trace amount of oxygen going in there to help support the production of the catalyst. The cell's running at about 1% atmospheric pressure. The amount of hydrogen we're flowing in here, if you burned all of it, it amounts to about 10 watts. But the oxygen that we're supplying would have to be 1/3 oxygen to 2/3 hydrogen in order to support combustion. In this case, the oxygen is very, very minimal. It's trace like 0.1% or 0.01% to maintain the conditions to generate the catalyst at the appropriate pressure and what they call a nascent state. That is not interacting with any other molecules or species. So then there's a molten metal injector in here that's injecting molten gallium against the counter electrode, and then there's an electrode at the top and the bottom, and that is running a high current through this, very, very low voltage, much lower than would be required to sustain a discharge plasma. But the high energy of the reaction, the hydrino, is causing that gas to ionize and create a plasma inside the cell. So we had a window in that cell. You would see brilliant light come out, and then we could thermal photovoltaic convert that. So down the bottom, you can see the electromagnetic pump that's pumping that metal in there and serving as an ejector and as a counter electrode for the 2-electrode system. So we're generating about 150,000 watts there, and that in our lab, you can go to our webpage on brilliantlightpower.com, and under what's new, you'll see that we have a boiler that we basically enclose this in a pressure vessel, and we can control the pressure between half an atmosphere and 15 atmospheres. So you can see quite a lot of steam coming out, and what we're going to do is we're going to turn that off because we don't want to overload the data center here with a thermal load. But you can see it's very, very profuse boiling as they brought it up to power. So about 150,000 watts, and we've ran validated systems, as I said, at 275,000 watts. So I'll just wait a second. So you can see that a little longer. Okay, we'll cut back to me. And I want to thank Rul Gandhi. He's a master's mechanical engineer from Rutgers, and Nashir Mehta. He's a PhD from Louisiana State. We thank you guys both very immensely for a good job on showing us the demonstrations. That was a demonstration of a new power source. You could put coal or gas or oil or nuclear uranium in there, and you could create heat as well. But this is being generated entirely from the formation of hydrinos, that is hydrogen going to a more chemically stable state. So it's a brand new power source. So phenomenal development and incredible implications for the world power industry. So going back to the thermal photovoltaic, we spent about $20 million on that program. We had Boeing Spectral Lab, Solero, Massimo, New Forge, National Renewable Energy Lab, Georgia Tech, Claflin, and many other participants, including materials companies that were involved with that required enormous amount of input. So we hit an impasse in terms of heating a black body radiator up to 3,000 degrees centigrade, and the photovoltaic manufacturers saying we were below 3,000, we weren't going to get any kind of photovoltaic efficiency at all. And then I was saying, well, if we could use light recycling, then we would get tremendously high efficiency. And turns out Boeing Spectral Lab scientists disagreed with me, and Massimo disagreed with me, but the Georgia Tech professor did agree, and he did a calculation that even we use a single junction silicon photovoltaic, even at 120 degrees centigrade, whereby typically the efficiency decreases as a function of temperature. So this is very high temperature relative to what solar cells are typically run at. But even at that, the projected efficiencies were 85%. So subsequently to developments of the thermal system, and in the time frame we were developing this thermal system, working out all the chemistry and the materials and the engineering systems. There's a paper published in the Proceedings of the National Academy of Science whereby a group from Berkeley and Caltech achieved 30% efficiency, not at 3,000 degrees, which they found they did it at an unbelievable low temperature of 1,200 degrees centigrade. So even at 2,000 degrees centigrade at a megawatt per square meter light intensity, that's a very, very viable approach for us to use black body emission, because it's very easy to achieve that temperature with the materials we're using. And better yet, even more recently, we've developed a window whereby we can have the transmission of the light directly through the window without metallizing over, so we can use the 3,000 to 5,000 degree black body radiation at intensities between 4.5 kilowatts and up to maybe even higher, that 60,000 or 50 or 60,000 times that of the sun. 3.5 thousand times the sun intensity on the Earth, concentration of the sun on the Earth, up to much higher values than that, depending on what temperature plasma black body radiation we use through the window. So then there's another system called magnetohydrodynamic that it's a new thermodynamic cycle that I invented, and there's thermodynamic calculations done in a paper with Mark Nansdale that is published on our webpage, and that has phenomenal capability. In fact, insane capability at 23 megawatts per liter power conversion. It works on the principle of what magnetohydrodynamic was really intended to work under, and that is a molten metal type design. So magnetohydrodynamic, there's quite a race during the 60s between the United States, Japan, and Russia to bring commercial magnetohydrodynamic to market. Russia had a plant at about 500 million watts using coal. But coal combustion gas is not electrically conductive, and you need electrically conductive stream in order for magnetohydrodynamic to work. Yeah, because that has a conductive stream going through cross that is perpendicular to magnetic fields and electrodes perpendicular to that, and that causes the generation of electrical power from that molten conductive stream. Well, it turns out they could never do that. They couldn't make a molten metal stream, so they relied on seeding combustion gases and basically expanded it through a nozzle to get it up to high kinetic energy, and then further expanded in an expansion chamber, or the MHD channel, to convert that into electricity. Efficiencies were low, and the ionization of the gases caused, or by seeding, was very, very inefficient. It turns out the conductivity was very, very low, about 100,000 to a millionth the conductivity of our current plasma, and the power scales according to the conductivity. So we actually have a molten metal stream in our case. It's molten metal and silver nanoparticles in plasma with tremendously high conductivity, and we can get it up to supersonic velocities and convert that directly into electricity. So what is the expansion efficiency? How much of the pressure volume energy in this reactor can be converted into kinetic energy? That's the key. It turns out it can be between 95 and 99%. The space shuttle nozzle, for example, is 99% efficient at converting pressure volume work into kinetic energy. Once you have a kinetic stream that's highly conductive, that can be converted into electricity, almost 100% efficiencies. This could be phenomenally efficient, less than $10 a kilowatt, unsurpassed power density. So it's something that we will work on in the future and continue to develop. But in the meantime, thermal photovoltaic is equally or like similarly very, very powerful in terms of conversion technology at a megawatt per square meter, extremely, extremely lightweight. And with this light recycling, we get up to almost 85% conversion efficiency, which in combination with the high sun concentration brings the capital cost of photovoltaics down to something on the order of $10 a kilowatt, extremely, extremely inexpensive, because you're taking, for example, $1,000 a kilowatt solar, dividing it by 1,000 because you're running that high concentration, and then you're dividing it again by not 7% more efficient, but 7 times is what that data shows with light recycling. Incredibly more efficient. And that dramatically simplifies the cooling systems and reduces the cooling load by multiples. So we have 2 primary categories of field of use. These are thermal applications and the SunCell for electrical power applications. Both are autonomous, the grids and fuels infrastructure. They have non-polluting, they're non-polluting as an energy source. They can use water as a source of hydrogen fuel. Tremendously low capital costs on the order of $30 to $40 a kilowatt. And they can be scaled over any range of scale depending on what the application is. Typically the thermal will start maybe 100,000 watts because it needs a power supply. When you put TPV power conversion on that, you could even go to much, much smaller units because you'd internally convert a portion of the power that would be required to run the ignition system. You'd do that on the system itself and not use external grid power, for example. And then completely autonomous of the grid would be the system with the TPV electric, and that would be DC, and then the user would then power convert the same as they do now with solar, because the output is identical to solar because we're using solar conversion. So the solar DC can be converted into AC or other types of voltage and current that's desired by using an inverter. So these are all standard component available parts that can be used for power conditioning if that is desired. Alternatively, you could just use DC because most of the loads currently in terms of consumer electronics, electric motors and lighting are all DC, like DC diode lighting, for example. So today's demonstration was the thermal SunCell with a steam boiler. So how it works is it has as I said before, it has a molten metal injector, injects molten gallium against the counter electrode. We run a high current through that. We get tremendous power from the Hydrino reaction. It heats up the gallium inventory, which is recirculated internally to about 1,000 degrees centigrade. And then that heat is transferred through the wall to the water and causes the water to boil. And then we can control that pressure in the reactor by controlling the size of the outlet or the aperture of the boiler. So we can achieve and controllably produce steam in the half atmosphere to 15 atmosphere range. So this boiler is operational in our lab now, and our goal now is to install these in industry to run pilot systems to prove the technology in an industry setting. So if you go to our webpage, www.brilliantlightpower.com, and go to What's New page, you can see a video of our steam boiler. So this is a validation just to show you some of the parameters involved, because we worked this out with the thermal system, the controllability and the scalability of the power, and this shows you from different parameters that we can use in addition to hydrogen flow and catalyst flow to control the power second to second or even millisecond to millisecond. So this is a validation done by Dr. Nan Steele. He has a PhD from the University of California, Berkeley. He works for the defense industry. He's a professor at UPenn, and he has tremendous credentials in terms of heat expert, particularly heat transfer expert, sort of unsurpassed of anyone in our circles. So we ran steam production over 100-hour duration trials, and let me show you some of the parameters that control its power output. So we run around 200 degrees centigrade molten metal temperature. The SunCell, this is the Hydrino component of power. This is the power produced by this new process that's maintained at SunCell, particularly the Hydrino power reaction. So it's about 25,000 watts. So then we turn, this is what the glow discharge or the fuel processor that activates the reactants, that was on in that cases. So another case, we'll turn that off, but we run it at twice the temperature. And now we see we got twice the power. Then we turn the power conditioning or the reactant conditioning system back on at the high temperature, and we ended up with now 4 times the original base case in terms of power production. Then we add 2 electrodes, and we repeat that experiment or that run, and we end up with 10 times more power than in the base case. So we know that temperature and current and the volume and the mechanism of how we maintain this reaction in terms of conditions we create, we can control this reaction to make pretty much any power level we want in combination with ganging the cells. So we really have a handle on how to control and scale this reaction. So this is a very exciting application, particularly the thermal photovoltaic. So the plasma is generated by the Hydrino process, and that can do one of 2 things. As I said, it could heat a black body radiator to a very, very high temperature. That's a little bit challenging, but if we run, there is a way we've subsequently developed that we have achieved 3,000 degree black body radiator of a radiator internally to the cell. Alternatively, we can run the cell at around 2,000 degrees centigrade and get greater than 50% efficiency. But even better yet, we can run 3,000 degrees to 5,000 degrees centigrade light through a window, and that can produce extraordinarily high power light and a spectrum that's very, very high efficiency, on the order of 85% efficiency, even at a single junction silicon photovoltaic, and give us a extraordinary power conversion system. So as I said before, the black body radiation is similar to a filament, but it's much higher area and it's comparable light as an incandescent light bulb. So that goes to a dense receiver array. A dense receiver array is a configuration of photovoltaic cells on a cold plate that takes away any unconverted power and removes that as heat. Again, because we have such high efficiency with light recycling, and because of the concentration of light, where the photovoltaic becomes more efficient as the light becomes more intense, the cooling requirements of the cell become very, very minimal. And that dramatically reduces the capital cost of photovoltaic conversion. So, as I was saying before, the infrared light that's not converted is reflected from a gold atomic layer on the back side of the photovoltaic, and it's reflected back to the black body radiator and re-emitted as black body radiation that has a very high component of photovoltaic active light in it, so it continues to recycle and dramatically increases your efficiency. So this is a cross section that shows a geodesic dome configured with dense receiver arrays. So we have patents issued worldwide, and uniquely, because there's so much resistance to this technology, because we were saying we could go below the atomic hydrogen ground state based on a theory that says there's no reality at the atomic scale. As far as I know, we have no known competitors. So it's a unique situation whereby we've gotten patents issued worldwide in this dramatic breakthrough energy technology. These are extremely comprehensive patents. They're about 300 pages a piece, and there's many of them worldwide in all the major energy markets in terms of where they've been filed. And they have about 150 figures, and they're extremely comprehensive. All the power reaction, the catalyst mechanism with its reaction, and the components of all the systems and power conversion systems and conditions and operating conditions and many features, and even product by process, the Hydrino products that are formed by the process of this chemistry. So very comprehensive, and it's possible, in my opinion, to operate the cell without all these different features that are disclosed in these patents. So we covered the live demonstration, so I'll go into commercialization. Basically, we're looking at a number of different markets. The thermal market, even at a reduced cost, is about $4.8 trillion a year. That is, we plan to sell thermal about half the current market. And similarly for electricity, even at that, there's 4.8 trillion addressable market in the thermal application and 3.5 trillion in the addressable electrical application. So this would be be initiated by using our steam boiler, that is the thermal market, and then the electrical market we use the TPV conversion initially, and maybe in longer term futuristic applications, and we would use it in different potentially defense applications, other exotic aerospace and space applications for the magnetohydrodynamic. There's a unique opportunity for passenger cars. In particular, you can look at a car, and let's say we sold the TPV SunCell that generated 150,000 watts continuously, 24/7, 365 for like 20 years. Let's say we sold that for $20,000. That market's about 100 million units per year. That would give us $2 trillion a year in revenue, and it's something we could separate off cars, passenger cars, and light-duty trucks. We could separate off as a separate market. For all the other markets, we're looking at. Let me cover this too as well. So if you look at a standard vehicle, say an F-150 pickup truck, which is the most popular vehicle in the United States. So on the sticker of that car, it'll say $2,000 a year is the annual fuel cost. So you take a 10-year lifetime of that vehicle, you're looking at $20,000. So the person that bought the vehicle would essentially get it for zero cost. That is, they get the SunCell for zero cost. It has no requirement for fuel refueling or charging, and tremendous power constantly, not only for 10 seconds, and about 1% the weight. So it's a phenomenal market draw for that particular product. We would have the OEM car manufacturers like Daimler and GM, whatever. They would be responsible for the maintenance and follow up on that particular product. Conversely, for the rest of the market, we envision doing leasing. Particularly, we'd have companies like Jabil, Flextronic, and others, Samina, that would manufacture SunCells under contract for us, and then we would have EPC firms, Henkels and McCoy, and others like Fluor and Bechtel and the like, that would install them and do maintenance and have depot repair centers. And they would do the installation. We wouldn't require FERC regulation because they're not connected to the grid, so it would require a local permit. They could put a preformed slab and put it in a day, just getting a local permit and hooking it as a piece of capital equipment like a generator. And we would treat it as anything like a bulldozer or a backhoe. It's leased equipment. So we would charge per diem, unregulated, unmetered power that we would supply for the customers. And the reason for doing that is a 150 kW cell could generate $150,000 worth of energy equivalent revenue. Typically, it's about $1 per watt per year. So that's a lot more than what we would sell it for example, in the car market. So it's so all their applications, big power applications, our model right now is the lease. And as I mentioned before, there's tremendous chemical applications for finally realizing a photonic computer, for example, because a Raman shows those fluxon linkages, because once you have a transition that can couple to the spin orbital coupling of the molecular hydrino, paired and unpaired electron interaction, you can have fluxon linkage in units of magnetic flux quantum, and that's the basis of a logic element, a memory element, or a sensor. There's many applications for that. As I said before, there's extraordinary properties these materials in terms of structural and material properties like magnetic properties and the like, and durability and stability and extreme conditions, and also the high rotational energy is enabling of a molecular laser, unsurpassed energy and power. So this is a summary of our go-to-market model. So we would lease initially 250 kW thermal units into industry and large commercial users, particularly multi-tenant residents would be in that category. And we do the same for electrical. We use large electrical power users, stationary electric, industrial, and commercial multi-tenant residences. And then ultimately, we would use the same approach as we go down to as we enter other more specialty markets like marine, rail, and the like. And then we could sell SunCells for automobile sales and light-duty trucks, but we would lease them in the case of bigger power applications, for more intense power applications like trucks and trains and ships and things like that we lease on a per diem basis. So let's get some of the timeline to introduce our technology. Particularly initially, we're going to install steam boilers as pilot plants in industry settings as we develop the TPV and the heated air application. So the boiler application is ready to deploy now in pilot systems, and then we're working with OEMs, particularly two of the best heat pipe manufacturers there are, to build components for us that would have the heat pipes and heat transfer system. So heat pipe's basically a closed pipe that has an alkali metal that boils and takes an enormous amount of heat with it as it boils compared to conduction and convection. And that condenses and transfers heat extremely efficiently along the length of the pipe and keeps that pipe essentially maintained at steady temperature. And then the heat fins receive that heat and we blow air through it and we end up with variable temperature hot air, 100 to 500 degrees C. So that takes the component manufacturers will make that system for us as a turnkey add-on to our cell. So that we project they'll have that ready very conservatively on the in the third quarter of 22. So we do the in 22 we're deploying steam boilers. By the third quarter of 23 we're doing the hot air heat exchangers, and then towards the end of 23 we're doing the TPV electric, which gives us plenty of time for the TPV manufacturers to make the dense receiver array as a component for us to add to the SunCell. So to summarize, there's invention. Summarize, there's the theoretical prediction of the Hydrino, and then the discovery that it matches many, many things in the cosmos. Its existence has been validated by many independent sources. Many labs have run analytical tests that unequivocally show there's Hydrino. The data is on our webpage under publications. There's a analytical presentation. There's also under publications a review article that goes through all these myriad, more than 22 different techniques that prove Hydrino. It has the linkages to papers we publish. We publish over 100 peer-reviewed journal publications, and we have an enormous number of incredibly definitive validations from industry and academic experts, and has links to all those references in those publications. The SunCell was invented to harness this enormous power that captures the 200 times energy release of a Hydrino formation relative to burning, whereby we can use water as the hydrogen fuel as a very, very pollution-free energy source, both on the fuel availability and storage and the power production ends of the business. So today's SunCell demonstration highlights our steam boiler SunCell. It's the most advanced, but the TPV is very rapidly coming in as we spin up that $20 million program where we had most of the engineering already developed, and we're going to bring that on very, very quickly as well. So this creates the ability to commercialize in direct commercial application for thermal, and also will very quickly bring on the electrical application. This technology has been validated by leading experts at the 300,000 watt level, producing radiation, and then additionally doing continuously cooling for very long duration tests, 250 kilowatt or more power producing steam. So on commercialization, our first goal is to pursue the commercial thermal, and also I mentioned the absorption chiller market. Turns out there are commercial devices, absorption chillers made by Trane and other types of other companies and big manufacturers of this equipment. And the absorption chiller uses steam to produce chilling, cooling. So you can use it for refrigeration, air conditioning, and things like cooling this data center. So those are the two big markets we can go after for space and process heating. Space and process heating and is about 25% of the world power market. The thermal market's about half the world's power market. And then in addition to that, there's the absorption chiller market, which is very vast as well. That we have a product that's applicable to those markets currently. So the SunCell boiler, the SunCell air heat exchanger, and the SunCell TPV electric power systems, they're all capable of being commercialized using known vendor supplied components. The corresponding bill of materials and cost of goods are in our business presentations. We have financials on these different products, and they show with about 6% market penetration, about 500 billion profit. The profit margins are absolutely extraordinary because the SunCells pay for themselves in about a week. So the cost of the bill of materials, cost of goods are on our webpage. If you're an industry customer and are interested in financials, we can provide those as well. We also have a use of proceeds of the very, very small amount of money it takes to bring this to commercial market in all the different verticals. So the launch commercialization currently, we're pursuing validation through industry testing of the boiler, and we're seeking partners. So we believe this is the most incredible energy technology the world has ever seen, and we think it will ultimately replace all forms of power, and it's truly greater than fire. Thank you very much for your time.